Hello, Sandamali, Mohammed. Can you all hear me? Hello, Sandamali.
Yes, sir.
Okay. Um, I think there's a slight delay in starting the session. So, sorry for that thing. And then we will start the session. Only two students available in the class. So, if possible, can you please share a message to your colleagues like the lecture will be started soon. So, I will wait until uh, to 10, right? So four more minutes. So ask them to start because I am going to start a new session for you all. So if you do not attend from the beginning, it may be difficult for you to understand these theories. So that's why I asked to join. So if possible, please share a message to your colleagues. Okay, I think it's time to start the session. So please inform your colleagues that the lecture has been started. So today we are going to start a new session that is stress distribution in soil. So this is a very important topic. That's why I was waiting for the others to join. So now, as you know, as civil engineers, what we are doing is we are creating certain additional stresses, right? So on the ground level, we are creating certain structures. So as a result, what will happen is there will be certain stresses exerted on the ground, right? So these stresses actually, as a result of these stresses, certain problems like the settlement and kind of settlement and a movement of the ground can be observed, right? So this so as civil engineers, definitely we have to create certain structures. So as a result, many stresses are exerted on the ground. So stress exerting is inevitable with respect to civil engineers, right? So any structures we create, any structures we build on earth will create certain stresses. So now what we are going to do is we are going to study the stresses. When we create certain stresses on the ground, what will happen? How these stresses distributed in the soil, right? So that's what we are going to study. So there are various theories. So we are going to study on those various theories. So starting from the simple principle, so I will discuss about some of the sophisticated theories regarding this stress distribution, right? So if you have any doubts, please let me know, because most of your assignments, most of your question paper, the questions in the question paper will coming from this part, right? So you should have to have a proper knowledge on this topic, the stress distribution in soil. Okay, so with that short introduction, I am going to step towards the presentation today. So first thing, what causes the stress in soil, right? So as I said, as civil engineers, we are creating many structures on the earth. So as a result, many stresses will be exerted on the soil. So when we think about how these stresses are generated, so in what form, what causes these stresses in soil, there are two forms, right? First thing is self-weight of soil. As you know, even last time we discussed about this part, we discussed that due to the self-weight of the soil, certain stresses can be exerted on the soil beneath, right? So now let's say you have created certain structure over here, a kind of embankment. So the soil here will have certain stresses, right? So you can see the sigma H is the horizontal stress, sigma V is the vertical stress. When we think about this sigma V will be there because of the self weight of this soil above this soil particle. Whatever the soil above this soil particle will have self weight of them. So as a result, certain vertical stress and horizontal stress can be there. So the first form where the stresses can be happen in soil is the self weight, right? The second form is we are creating certain structures. So as a result, certain additional stresses like delta sigma can be exerted on the soil particle, right? So there are two forms, very clear. First thing is the self weight of soil above the soil particles we are considering. That is the first thing. The other thing is there are many external structures that we are creating as civil engineers. So as a result, there are certain additional stresses like delta sigma. So if somebody asks you what causes the stress in soil, you have to answer with two answers. So the first answer is the self weight of soil. The second answer is the external loads, the structural load, external load. Likewise, there are different types of loads. So as a result of these various kind of loads, these kind of additional stresses can be induced in the soil particles, right? So that those are the two forms. Okay, moving on. So now when we are thinking about the stresses due to the self weight, right? Stresses due to the self weight. So actually what happened is when we think about this soil particle, there is a certain soil mass above this soil particle. There's a certain soil mass above this soil particle. Okay. So, what happened here is now because of the soil mass above the soil particle, certain stresses can be happen, right? So, the vertical geostatic stress at any depth, right? The geostatic stress means the weight of the soil above this depth, right? Above this depth, there is a soil mass. As a result, certain weight will be acting on this soil particle. So that we called as geostatic stress. So how to calculate that one? That geostatic stress can be calculated by this simple formula, right? So sigma is equal to gamma Z. Z is the depth from this ground level to the point we are considering here, right? Depth from here to here. And gamma is the unit weight of soil. So if you multiply the unit weight by the depth we are considering, so that the stress, vertical geostatic stress can be calculated, right? So that's how we are going to calculate the stress due to the self weight of the soil mass, right? The other thing, that moving on to the next slide. Now let's say, so this is when the soil is constant. The unit weight is not going to be changed in this depth. So the soil will not be changed in this depth. In that situation, you can multiply the gamma, that is the unit weight of soil, into the depth. But in the case where the soil varies, now from here to here, if the soil varies, so in such situation, what we have to do is each and every soil particle, there is a different gamma value. So that gamma value into that small depth particle. Likewise, we have to add everything. I repeat, now let's say the soil type is varying from the depth. Here at first centimeter, we have one soil. In the second centimeter, we will be having another soil. Third centimeter, we will be having another soil. Likewise, from the depth, what will happen is soil will be varied. So in such situation, how to calculate the stress at this point due to the self weight? So the calculation method will be gamma into that small depth, let's say 1 centimeter, gamma into that particular depth. Then another gamma will be there because the soil is different. So that gamma into that particular small depth. Likewise, we have to add from gamma dAz from here to here. That's what I did here. So gamma means the small for a given small depth, the unit weight. Now the soil will be varied from place to place, but the soil will remain constant in very small depth. No, so that gamma into d is hello. So in that situation, gamma into d is at, we say sigma within that small depth portion, right? So then we have very small depth. There are from here to here, 0 to z. So that's why I made it as integration sign. So gamma dz from 0 to z. So this has been happen because the soil will vary from here to here. From instance to instance, the soil is vary. So in C situation, now B situation is soil varies continuously with depth. So in such situation, we have to integrate the gamma dz value. So within the small depth, you have to calculate the gamma dz and integrate from 0 to z. So that's what we have to do. The other thing is, for the stratified soil, means layered soil. Now there are many layers. So first, let's say first 300 millimeter you have clay. Another 300 millimeter you have sandy soil. Again 1 meter you will be having another soil. Another 500 millimeter you have another soil. Likewise, layer wise there are soils. So such kind of situations are commonly available in Sri Lanka and the countries like Sri Lanka, the stratified soil. So in such situation, what we have to do is gamma into that particular depth. You have to uh, calculate the gamma into delta z, and then you have to get the summation from here to here. Then only you can get the self weight due to that soil. So we will have an example on this situation so that you can understand this situation well. Right. Received a message. Right. Can't you see my screen? Mohammed, still you cannot see my screen?
Yes, yes, it's showing only blank. No,
Ah,
it's showing
really?
only
How
blank.
about the others?
Yes.
Others also you cannot see my screen? Mohammed, now you can see.
Yes.
Now is it
No,
possible
I'm
to
not
see?
able to see.
How about the others?
No, no, it's only.
Asha, Pranmini, Vijay Kon. Pranmini, can't you see my screen? From my side, I have shared my screen and it is visible that you are seeing my screen. So how about the others? Right. I think it's visible, no? Okay. Okay. Right. Yeah, right. So then I hope it is clear to you. This is the point I was discussing. So in the case number A, when we are going to calculate sigma V, uh, the vertical stress due to the self weight. So if the soil layer is not being changed in that situation, it is very easy. So you have unique soil. You have one soil above this soil particle. So in such situation, what you have to do is the gamma will not be changed from here to here, so that gamma into this depth. So we have the stress due to the self weight then. Okay, that is case number A. When we are talking about case number B, the problem is now this soil varies from here to here. So soil will be changing from here to here. So in that situation, we will divide this soil into very small depth. So depth of that small soil layer will be DZ, right? So as you know, within that DZ a very small depth, the soil properties will not be changed. So by assuming that the soil properties will not be changed within that dz, so as you know, gamma into dz is the weight of that small layer, right? And likewise, you have to add each and every layer from here to here. That's why the integration happens, right? From 0 to z means 0 is here, z is here. From here to here, you will add each gamma dz value from here to here. So the case number C is the stratified soil, means the layered soil. So there we are having um, certain layers. Within that layer, the soil properties will not be changed. Let's say there is a clay soil. in first 500 millimeters. Another 1 meter you will be having a sandy soil. Likewise, within that particular layer, the soil properties will not be changed. So in that situation, gamma is the unit weight of that particular layer, and delta Z is the depth of that particular layer. So likewise, each and every layer you have to calculate delta Z value and add together to have sigma V value. So those are the three cases so that we can obtain the geostatic stress. In other words, the weight or the self weight due to this soil at this point. Okay. So those are the three cases. So I am going to discuss a example. So now we are having a stratified soil layer. So the point of interest is somewhere here at point X. As you can see, so this is the ground level. From this ground level, the first layer is sand and the second layer is clay. And groundwater table will be there. So as you know, the gamma value will be different here because it is dry sand. Here we have wet sand, saturated sand, because the groundwater table is here. So as a result, the gamma values will be different here and here, right? So you have been given with certain values over there. The sand gamma D is 13.1 kilonewtons per cubic meter. Sand gamma is 18 kilonewtons per cubic meter. And we have clay layer here. Clay gamma is 19.8 kilonewtons per cubic meter. So now there is certain layered soil above this point X, right? So if somebody asks you to calculate the stress due to these soil layers, now how to calculate, right? So I discussed this is the case number C. So different soil layers are available. Here we have a dry sand layer. Here we have a saturated sand layer. Here we have a saturated clay layer. So if you know the gamma values of the each and every these layers, so what you have to do is gamma into depth so that you can evaluate the stress coming to this position. So can you do it? I will give you 2-3 minutes. Huh? If you can try, please give me the answer. So it's very easy. So I will give you a little time. Try to calculate the final value, final stress at point X. If you get any answers, can you please share through chat box? It's really simple, no? First, we have a dry sand. So the gamma value of that dry sand is 13.1. So gamma into D, gamma into H. So that would be the weight due to this sand layer. So that 13.1 into 2. Here 2.5, that is the saturated sand layer. Their gamma is 18. 18 into 2.5. So that you can get the stress due to this layer. And the clay, we have 19.8 into 4.5, so that you can get the stress over there. So if you add all together, you can get the final stress at point X. So this is the total stress, 13.1 into 2, 18 into 2.5, 19.8 into 4.5. So that the total stress at this point is 160.3. That is the total stress. So another thing is you cannot forget the pore water pressure, right? So the pore water pressure here is U is equal to gamma W H2 plus H3, right? Because the water will be here, the water table will be here, so that the water itself, it has certain additional stress up to here. So the height is 2.5 plus 4.5. So 2.5 plus 4.5, altogether it is 7 meter into 9.81, right? So instead 9.81, I got 10 for my easiness. So that U will be 70 kilonewtons per square meter. Now you know total stress, you know pore water pressure. If you want to calculate the stress due to the soil, what would be the answer? The effective stress will be 90.3 kilonewtons per square meter. So some questions refers to the total stress, some questions refers to the effective stress. So you have to select what is stress to be used, right? So the self weight at this point due to the soil will be 90.3, right? Due to soil 90.3, the pore water will be 70, the total stress will be 160.3. Okay, so hope you get a clear idea now. Any problems up to this point? Because we have many things to cover. If you don't have any problem, we will proceed. If not, please let me know, I will clarify a little further. Hello,
Hello, sir.
is that
Yeah,
clear to you
18
all?
into 2 or 2. Yeah,
Sorry.
I just want to know the 18 into 2 or 18. 18 into 2 or 2.5.
All right. Let me clarify, Mohammed. Thanks for your question. Now, here, gamma D,
Okay.
dry unit weight. Here, gamma, that means the bulk unit weight. So, as you know, here we have the groundwater table. So, from here to here, we will be having a saturated or kind of wet soil there. So, when we are using the unit weight, we have to use the gamma for this layer. So, 18 will be applicable to here. Now, this one, it is dry soil. Gamma D means gamma dry. So, in that situation, we have to use 13.1. Okay. Okay, Mohammed.
Yeah, okay, sir.
Since
Thank you for your
uh,
information.
okay. So the soil, the first topsoil layer, it will be dry soil. That's why we have to use this gamma D for that particular layer. But this soil will be wet soil. That's why we are using gamma value. Gamma means the bulk unit weight we will be using for this one. So that's why 18 into 2.5 over here and 13.1 into 2. Okay. So we will move on then.
If there are no other question, any other question? Asha, Ranmini, Sandamali, are you all okay?
Yes, sir.
Okay, okay, right, Ranmini. Okay, now moving on to the next slide. Now I am going to little additional things, right? Now, these things are all these things actually we have discussed in your previous studies. Not me, some of other lectures, like you have completed your NDES, somebody NDT, somebody HND. So those things were there in your previous studies. Just this is just for a kind of reminding session for you. Now, from here onwards, you should understand properly, because your questions which are there in your exam paper will depend on from this slide, right? So from this slide onward, you will have to get a better knowledge and better understanding. So if you don't understand these matters, please let me know. I will clarify, right? So now what we discussed so far is the stress due to the self-weight of the material, self-weight of the soil mass. Now we are going to discuss about the stress due to external structures or external loads. Now, let's say we have created the foundation over there. So rectangular foundation is here. So it is obvious, no? Once you created the certain foundation on the top of soil, certain additional stress will be exerted in addition to the self-weight of the soil. Self-weight is already there. In addition, you are creating certain additional structures. So due to those structures also, what will happen? Certain additional structures, additional stresses will be exerted on the ground. Okay. So now, let's say a rectangular footing is here. The point load coming from this column is P, capital P, right? So we have a term called contact pressure, a term called contact pressure. So what we are referring to contact pressure is the pressure at this surface where the foundation and the ground is contacting with each other. I repeat, the pressure at this surface where the foundation and the ground is meeting each other, contacting each other. So the stress, it's really easy. If you can recall your O-level studies, how to determine the stress, how to determine the pressure, force divided by area. What is the force here? Here the force will be capital P. So what is the area here? Now this is a kind of rectangular footing. So the contacting area will be breadth into the length. Diga වැඩි කිරීම පළල. So that would be the area, contacting area. So now we have breadth here, length on the other direction, right? So the contact pressure will be P divided by B into L. P is the force, B into L is the cross-sectional dimensions, so that we can get the area, cross-sectional area of the rectangular foundation. Okay. Now, it is so much clear how to evaluate the contact pressure. Contact pressure is P, that is the force coming from this column to the foundation, right? So that force will be transmitted to the ground through this foundation. Okay. So now P divided by B into L, that would be the contact pressure. So sigma naught is the contact pressure, P is the point load, and B into L is the contact area, right? So very simple. Contact pressure means the foundation is there. Foundation is the member where this load, the structural load will be transmitted, will be contacted to the ground, right? So that contact pressure is P divided by area, force divided by area. Force is P, area is B into L, right? Very clear. Now, moving on. Now, our problem is contact pressure you can evaluate. But if somebody asks you to evaluate what is the stress 10 meters below the foundation level, what is the stress 2 meters away and then 5 meters down this point, what is the pressure? 2 meters away from the foundation corner, but 5 meters down. So at that point, due to this foundation, what is the pressure? So those kind of problems are there, right? I will show you one example. Now, if somebody asks you, okay, there's a pipe here, right? So from here to here we have 2 meter. Okay. From here to here we have 10 meter. So as a result of this foundation load, what would be the stress on this pipe, right? So those are the practical problems. So many problems can be there. So in Sri Lanka, as you know, there are CMC pipes, right? Sewer pipelines, water pipelines. When we are going to do certain structures, right? So but we cannot omit uh, our structures to be built over there. We have to definitely build our structures over there. So because of this pipe, we cannot hold our construction. Okay. So in such situation, what we have to do? Definitely we have to construct this one. Then we have to check whether this pipe is okay with this additional stress due to the foundation. That you have to calculate, right? That you have to calculate, right? Now the pipe is there. Anyway, you have to construct this foundation. As a result of this foundation, will there be any impact on this pipe? That you have to calculate. If there is an impact, what you have to do is, you have to do certain improvement over here. And if there is no impact, you can neglect and you can proceed the construction. Okay. So those things can be done with certain other theories. Now you know how to evaluate the contact pressure. Now we are going to discuss how to evaluate the stress other than this contact pressure due to this foundation. The stress other than this contact pressure due to this foundation, right? Okay. Now, stress distribution in soil with depth, right? Stress distribution in soil with depth. With depth, what will happen? Now you know contact pressure will be somewhere here. This is the contacting area of this foundation, right? So that soil will be transmitted with certain additional stresses from this foundation from here onwards, right? So, how to determine the soil stress distribution with depth? So, there are two principles. First thing is, when you go down, means when the depth increase from there, right? Let's say 1 meter, 2 meter, 3 meter, like that. When you go down, the stress impact will be reduced. The stress impact will be reduced. That means here you have contact pressure. Contact pressure is the highest pressure. If you go 1 meter down, it will be lesser than this contact pressure. If you go 2 meter down, it will be more reduced, right? If you go 3 meter down, it will be more reduced. Likewise, if you go more down, there will be a point there, your additional stress will not be much impacted. Okay. So the other principle is, if you go radially, if you go radially from the point of load, the intensity of stress will be reduces, right? I repeat, if you go vertically down, your stress will be going down. And if you go radially down, what will happen? Your stress will be reduced. I will show you. It is like this. Now let's say there is a contact pressure 200 kilonewtons per square meter. But if you go down, it will be reduced into 160, 140, 120. Likewise, it will be reducing. So now here, radially also, it will be reduced in the same way, right? Vertically, it will be reducing, and radially also, it will be reducing. Okay. With that principle, we have three different theories to evaluate how this stress distribution happens, right? Now, due to the various external loads, how to evaluate this stress distribution within the soil mass, right? Now, let's say a point load Q is applied, and as a result, how will be the stress generated at the point there, at the point considered in this position. So we have three theories for that. First theory is approximate method. Second theory is Bosonics theory. Third theory is Westergaard's theory. So we will be discussing all three in this class. Today I try to complete at least approximate theory and part of Bosonics theory, and tomorrow we are going to continue the balance part of it. So that's my plan. I will try to complete the Bosonic up to Bosonic theory. Okay. So moving on with the approximate method, right? So approximate method is a kind of very simple method, right? We can use this theory for our problems in civil engineering, but the result is like more conservative, right? It's more safe, right? If you go for Bosonic theory or Westergaard theory, what will happen? A kind of realistic value can be obtained. But if you go for approximate method, a more safe value, huh? More safe value will be there. Like, let's say now Q load has been applied over there. If you calculate the approximate, if you calculate with the approximate method, so let's say Q is equal to 200 at 2 meters down and 5 meters away. This is the point. So if you calculate with the approximate method, the stress reduction may be around 100 kilonewtons per square meter. Here you have 200 kilonewtons per square meter as the contact pressure, but here it comes as 100 kilonewtons per square meter. If you use the Bosonic theory to evaluate this one, the value may be little bit safer. Like now in approximate method, you will be having 100, but Bosonic theory, you will be having like 80. Westergaard theory, something like 85, right? So approximate method will give you a higher value, so that you will be designing your design philosophies and your structures in a higher value. Means what will happen? Your rebar will be much, your foundation sizes will be much, so it will be more conservative, right? So that we can use as civil engineers this approximate method, but we have to reduce the usage because it is more conservative. right? Okay. The approximate method. Okay. Now, as you know, this is a rectangular footing. So this is a section of the footing. So this is the column. So the load coming from the column is Q, capital Q, right? So in this situation, what is the contact pressure? Actually, this should not be P. This should be Q, not P. This should be Q. Okay. So what is the contact pressure then? Q into this contacting area. So this is the plan area of this foundation. So the plan dimensions are B into L. So that's why contact pressure, as previously we discussed, Q divided by B into L. Okay. Now, what happen if you use 2-to-1 method for stress distribution? Let's say we are now referring Z meter down this 14. So in that situation, what is the distributed pressure at depth Z? So it will be given by this formula. Q divided by B plus Z into L plus Z. Okay. So Q divided by B plus Z into L plus Z. So it's very easy, right? So this is the formula, right? So contact pressure, how to evaluate? Q divided by BL. Now how to evaluate the stress at the depth Z? It is very easy. Q divided by B plus Z into L plus Z. Z is the depth from here to here for the considered point, right? Q is the point load, right? So all those things are very clear and the evaluation method also very clear. Let's say you are having 100 kilonewton point load here and B and L is 10 meter by 10 meter. So 100 divided by 10 into 10. The contact pressure will be 1 kilonewton per meter square, right? Got it? Q is 100, B is 100, L is 100. Sorry, Q is 100, B is 10, L is 10. So in that situation, 100 divided by 10 into 10. That would be the contact pressure. Contact pressure is 1 kilonewton per meter square. Now, if somebody asks you to calculate the pressure at 10 meter down, the pressure at 10 meter down. So in that situation, 100 divided by 10 plus 10. Here B is 10, Z is 10, L also 10, Z also 10. Then 100 divided by 20 into 20. 100 divided by 400. So that the answer will be 0.025. Okay. So hope you understood the example. The contact pressure is 1 kilonewton per square meter, and at 10 meters down, you will be having 0.025 kilonewtons per square meter. Okay, understood? Is that clear? Approximate method. Kanmini, Asha, Muhammad, is that clear?
Yes, sir.
Sandamali? Okay, right? Because last time I discussed all the here this principle also. So some of you were performing well in the exam, but somebody they didn't understand the principle. But in the class they say it is understandable, right? It is okay for them. But anyway, at the exam they didn't perform well, right? Most of the students perform well, but few finds difficult to understand even this simple principle, right? So in this situation, if you have any problem, please let me know. So if you don't have any problems, we will move on. So I am going to now show you how this formula comes. Now it is like this. Now here we are having a contact pressure Q naught over here. Simple Q naught, that is contact pressure. What we referred to in this previous slide, here we have capital Q. Capital Q is the point load coming from the column. The point load coming from the column. But here what happened was, we are now giving the contact pressure. Q naught, simple Q naught. So don't make problems in your mind. Previously we are discussing regarding the point load coming from the column. Now we are discussing about the contact pressure. Okay, so now I converted that. Simple Q naught is the stress, point load is equal to stress into area, so that point load here Q naught into BL. Is that clear? Stress Q naught, area B into L, right? Foundation is B into L. So that is not the story we are talking. We are talking about the stress at this point. How to evaluate? Now I said the approximate method, or else we can say 2-to-1 method. 2-to-1 method, right? Means vertically, if you go 2 meters down, horizontally, the distribution will be 1 meter. I repeat, 2 vertical to 1 horizontal means if you go 2 steps down, distribution is 1 meter horizontally, right? So likewise, if you go Z meter down, horizontally what you have to do go is Z divided by 2. I repeat. Now if you go 2 meters down, 1 meter horizontal. If you go Z meter down, that means Z divided by 2 horizontal distance. So in this direction also you will be having Z divided by 2 if you go Z meter down, if there is 2-to-1 stress distribution. So this direction also the similar happens. If you go Z meter down, here also it's divided by 2, right? So in that situation, if somebody asks you to if somebody asks you to decide what is the stress over there, right? The point load will be capital Q. So capital Q will be Q naught into B into L. Here also the point load same. Here also the point load same. So point load will not be different. So Q naught into B into L, that would be the point load at this point, and also the point load at this point. The difference from these two here is, here our length is B. Now here we have B. From here to here we have B. I will draw something. From here to here we have B. This is B. Additionally, we have Z divided by 2 here, and here also we have Z divided by 2. Z divided by 2 plus Z divided by 2 means Z. So that's why from here to here we have B plus Z. B plus Z. Hope you understood now. Here B, we have the horizontal distribution 2-to-1 here. If you go Z down, that means from here to here we have Z divided by 2. So Z divided by 2, Z divided by 2 plus B, it means B plus Z. Okay. So this is B side. How about the other side? That means L side. L side also it is similar. Here we have L. So similar way there will be the stress distribution. There also we will be having L plus Z. L plus Z. Okay. Here we have L. here we have L plus Z. So that's why this is actually a point load. Don't worry about this. This is capital Q. Okay, this is capital Q. I mentioned here, no? Point load is Q naught. This is the contact pressure into B into L is the point load. So that is equal to capital Q, which is we discussed short while ago. Capital Q. See, capital Q. That is the point load. So this one is the point load, right? So with this point load, we have B plus Z into L plus Z as the area, because the area here B into L, but here we have a distributed area. The distributed area is B plus Z in this direction, L plus Z in this direction. So that delta sigma is equal to Q divided by B plus Z into L plus Z. Is that clear? Is it clear how this formula comes? Hmm? In my first lecture, I mentioned it's better if you have a kind of um you know this. If you discuss with the lecturer, it would be very easier for lecturer to carry out the lecture, right? So I always say, Asha, Mohammed, Ranmini, Sandamali, you all are professionals, right? You all are working in the industry. So if something is there, if something to be clarified, if it is fine to go with, please let me know, so that without taking much time, I can carry out the lecture. Okay. So we can cover more things within today, right? So I hope that is clear with this explanation, right? I will move on. If you have any doubt, please let me know later, right? So now we have an example here. P is 1200 kilonewton, B is 2 meter, D is 3 meter. What you have to decide is the contact pressure at this point, the contact pressure, and using the approximate method, evaluate the distributed stress at 1 meter below the footing bottom level, evaluate the distributed stress at 5 meter below the footing bottom level, right? So can you give a try, right? If possible, please try on it. I will give you a kind of 5 minutes. So it's very much enough. Try to memorize all the things, right? So um, this is the formula. So the P is given as the point load. So point load, if you know the contact area, contact pressure is very easy. And then what you have to do is distributed distress at 1 meter below the footing level and distributed distress at 5 meter below the footing level. So please try on it. I will give you 5 minutes. Okay. Okay, then shall we try this one? Right? Okay. Now we have first question is contact pressure. So 1200, that would be the point load. 1200 divided by the contacting area. Contacting area is 2 into 3, right? 2 into 3. So the answer is 1200 divided by 6, right? So the contact pressure is 200 kilonewton per square meter. I hope everybody got that answer, right? So kilonewton per square meter. What your previous batch did was, once they complete with the answer, they send me their answers in the chat box so that I can refer to those answers and inform them whether it is correct or not. So I prefer if you do the same so that you can actually check your answers with me, right? Using the approximate method, evaluate the distributed stress at 1 meter below the footing level. How to evaluate? It is very easy, no? Q divided by B plus Z, B plus Z, right? Into L plus Z, right? Okay. So this is the formula for approximate method. I discussed with you how these formulas are there and how to derive this formula. I already explained to you. So how to do? Now Q is 1200. That is no change with this contact pressure calculation. The change is the Z value, right? B is 2 and then 2 plus 1. L is 3, 3 plus 1, 3 plus 1, right? So what will happen now? 1200 divided by 2 plus 1 into 3 plus 1. 2 plus 1 is 3, 3 plus 1 is 4, 3 into 4, 12. So that the value will be 1200 divided by 12. It will be 100 kilonewton per square meter, right? So you can see at the contacting point, the stress is 200 kilonewton per square meter. And if you go down 1 meter, the stress will be reduced by 2. Stress here 200 and here 100. So the stress has been reduced by 2, right? Means uh, the 200 value is there at the contact pressure. If you go 1 meter down, it has been 100 kilonewton per square meter. So if you go 5 meters down, what will happen now? So the same principle, only the values will be different. So now what will happen? 1200 divided by 2 plus 5, 2 plus 5, right? Into 3 plus 5. So you can calculate the answer. 3 plus 5. 3 plus 5 is 8. 2 plus 5 is 7, right? 1200 is there. So the value will be, anybody got the value? 1200 divided by 56. 21.43. 21.43. Right? So the units are kilonewton per square meter. So you can see at the contacting point, the stress is 200. And if you go down 1 meter, the value will be 100 kilonewton per square meter. And if you go 5 meter down the contacting point, so the stress value will be 21.43. So gradually the stress will be reduced, right? So I hope that is clear, this example. So any doubts or anything to be clear? Let me know. If you don't have any problem, shall we proceed? Hmm? Is it clear? Okay. Mohammed, clear, no? Ranmini, thank you. Thank you for the reply. And the other person, I received another message, Sandamali. Good. Okay. So that's all for approximate method. So I hope everything is clear with you. Now, how about this one you know already? The rectangular foundation you know already, and you know the formula. Q divided by B plus Z into L plus Z. The strip footing is something different. Strip means the length is too much compared to the breadth. The length is too much. Think of an retaining wall. Width is there around 600, 1 meter sometimes 1.2 meters. Likewise, the width is there. But the length compared to the width, it's too much. It's really long. Think about kind of strip foundation, inverted T-type foundation or something like that. So there also we will be having the same principle. So in this situation, what we will do is we will keep the length as a unit, right? So it will be a unique value, a unit value, so that the stress will be calculated from this equation Q divided by B plus Z, and the length portion compared to this one, it is too much high, so that we will not consider that part. So the value will be kilonewton per square meter per meter. I repeat. So the unit of this stress will be kilonewton per square meter per meter. The length will be given as per meter. Okay, this is kilonewton. Kilonewton per square meter per meter. So that would be the value from this one. But here, kilonewton per square meter, no issue. Per square meter. Okay. So, is that clear? Now, a kind of very informative or very illustrative image is here. So you can see stress on this plane. So this is the contacting area. You see this contacting area is B into L. So that's why the stress is coming like capital Q divided by BL. The area is BL, but the distributed pressure, the distributed pressure in this area, the distributed area is B plus Z into L plus Z. So the same Q will be applicable, and B plus Z and L plus Z is the additional area. You see, not only B plus Z, L side also the distribution is there, right? So a kind of very informative diagram to illustrate the approximate method. Okay. So that's all for approximate method. So I will show you a kind of example. Uh, Let me show you. This is your past paper. I will show you an example. So you see, a two-story building features a square-shaped footing that supports a column load at its center. The column load has a magnitude of 1000 kilonewton, and it can be assumed that the load is applied as a point load. The planned dimensions of the square footing are 2 meter by 2 meter. Utilizing the approximate method 2 to 1 method, determine the distributed distress at a depth of 2 meter below the found footing level. You see? So if you understood this principle, you can earn 8 marks. So this is the question paper 2023, right? And then 2024, 2023, I had another batch. So that batch also I remember I I had another, let me see, 2023. So this is the question paper, sorry, 2022. So this is the question paper for 2022. Hope you can see. So there are also, as I remember, I put one question on that area. You see, a rectangular shaped footing of a three-story building carries a column load at its center. The magnitude of the column load is 2500 kilonewton, and it can be assumed as a point load acting on the center of the footing. The planned dimension of the rectangular footing is 2 meter into 2.5 meter, right? Using the approximate method, calculate the distributed distress at 2 meter below the footing level. You may develop required equations for above calculation. Okay. So in your exam paper also, similar kind of questions can be expected, right? I will show you 2024 one also, right? Exam paper, the previous batch exam paper. There also, as I remember, I put one question there. No, I didn't put any question. Here, using approximate 2 to 1 method, evaluate the stress at mid depth of the clay layer 5 meter. Sorry, 5 marks are there. So in each of the question paper, this approximate method will be used and you will be questioned, right? So it's really much important for you to understand that principle properly. So I covered that principle. So hope you can hope you got a kind of certain knowledge so that you will be answering the question papers well, right? So moving on to the bosonics theory, right? So this is not like approximate method. Actually, approximate method is very straightforward method, very simple method. But bosonics theory is somewhat different. Different means there are there are few assumptions, and also the derivation processes are there for the formula. So here the nice story is, I'm not going to give you the derivational part. No need to study that thing. You just need to know the equations So in the question paper, don't worry, I will give you all the equations. What you have to do is you will have to understand the principle and use it properly at the exam paper. Plug correct values on the equations and get the final answer. That's what expected from you. Okay. So these are the assumptions for Bosonics theory. These are the assumptions for Bosonics theory. Okay. So Bosonic in 1885, he has solved the problem of stress due to certain external loads, right? So external load is applied. You can see, right? Hope my um, presentation is visible to you. So what will happen is external Q load is applied. This is a point load. So Bosonic has solved this one with the geometry and the application of the knowledge of stresses. He has solved this problem, and then he has made several assumptions for this one. During the derivational process, he has made several assumptions. So the assumptions are the soil mass is elastic. Actually, as you know, soil is not a elastic material, but Bosonics in his derivation process, he has assumed the soil to be elastic material, and also soil is isotropic. That is the another assumption, and homogeneous. Do you know the difference between isotropic and homogeneous? Do you know the difference between these three words, elastic, isotropic, and homogeneous? Somebody? So actually, elastic is a kind of a material with elasticity properties, right? So let's say if you apply a tensile force in elastic material, what will happen? Huh? Once you remove the load, it will regain its original shape and original length, right? If you apply a tensile force on a material, on an elastic material, what will happen? It will change its shape and length. But if you remove the force, what it should be is uh, it will regain its original position and original shape. The length will not be changed. So that is the elastic principle, right? Isotropic is if you get a soil point, the properties will not be changed in every direction. In every direction, the properties will not be changed, right? Homogeneous means within a layer, the properties will not be changed, right? The properties will not be changed. So those are the definitions of these properties: elastic property, isotropic properties, and homogeneous properties. So none of these properties are available in the soil mass. As you know, soil is not a elastic material. Soil is not a isotropic material. Soil is not a homogeneous material. Also, soil is not a infinite material, right? So Bosonic, anyhow, to develop his theory, he has assumed the soil mass as elastic, isotropic, homogeneous, and semi-infinite material. Also, he has assumed that the soil mass is weightless, right? Soil mass is weightless. That is his assumption. And the load is a point load acting on the surface. So these are the three assumptions that he has made. So the Bosonic, with these three assumptions, he has solved a problem so that once you apply a Q point load there, he calculate the delta sigma Z value at the soil point beneath this soil, right? So when you see this geometry, you can see it is a 3D Cartesian coordinate system. 3D system. So 3D coordinate system, we have x-axis here, y-axis here, right? So think in a 3D coordinate system. So this point has been there in the space. So this is where the point load is applied. And then we have the origin of the coordinate at this point, right? The origin of the coordinate system is at this point. So we have x dimension along this x-axis, so that this is the x dimension, and y dimension along the y-axis. So the diagonal length will be r. From there, if you go down z dimension, you can find this point. I repeat, along the x-axis, you go x distance. Along the y-axis, you go y distance. And along the z-axis, you go z distance, so that this soil point will be there. So if you get the shortest distance from this origin to this point, the 3D dimension will be L. Is that clear? I repeat, this is the coordinate system. This is the point load. So at the point load, we start our coordinate system x, y, z. So if you go x dimension along the x-axis and y dimension along the y-axis and z dimension along the z-axis, you will find your soil point, right? So if you get the 3D shortest distance from this origin to this point, the length will be L. So you should understand this coordinate system well. Okay. So if you get a plane, along this L dimension, that is there. So this is the L dimension point. So what we have done was, we cut a plane along this surface and then make this diagram. So that point load will be acting there, Z dimension down, you have R dimension horizontal, and the diagonal distance is L. Okay. So with that understanding, let's move to the next slide for our formulae. Now, bosonic equation for point load, it will be like this. So the Q point load is applied there, and X dimension horizontal distance, Y dimension along Y direction, Z dimension if you go down, you will be meeting your soil point there. And then what is the delta sigma Z due to this Q at this soil point? This is the delta sigma Z. So if you want to calculate the delta sigma Z due to this point load Q, it will be 3Q Z cube divided by 255 L into the power of 5, right? I repeat, delta sigma Z is equal to 3Q Z cube divided by 25 L to the power 5. Now, so I rearrange the terms 3Q Z cube, no change. 25, what is this L? L is the shortest 3D distance from this origin to this soil point. So in other terms, what is R? R is the diagonal of this coordinate system, diagonal distance. So you see, from here to here we have X, from here to here we have Y. So if you know X and Y, you can evaluate R. So the R distance using the Pythagorean theorem, so you know R is equal to square root X square plus Y square. That is very clear. So what would be the L then? So L means as you know, here R is square. Here we have R. Here we have Z. So L square is R square plus Z square. I repeat, L square is R square plus Z square. Okay. Now R square is X square plus Y square. That's why L square is equal to X square plus Y square plus Z square. So if you want to calculate L, square root S square plus Y square plus Z square. Right? So that's why I mention here, instead of L, R square plus Z square. R square plus Z square into 5 divided by 2. 5 divided by 2. Why it is so? L is equal to square root R square plus Z square, no? That means R square plus Z square, the power half. Square root is equal to power half. So now here, R square plus Z square, that is for L, and here we have a power 5. It should be divided by 2 because of this square root. I hope this is clear to you, so that due to this point load Q, we can calculate the delta sigma Z using this formula. So this is the bosonic equation. Okay. So now this is for delta sigma Z. Actually, in most of our soil mechanics, geomechanics problems, we are now concentrating on only on vertical stress. But if somebody wants to calculate delta sigma x and delta sigma y, he can calculate that using this formula. So I am not going to discuss about this formula. This is for your information and knowledge purposes only. So this is also been developed by the bosonic. So here delta sigma Z is given by this equation, and delta sigma x is given by from this equation. So we are only focusing on this equation only, right? I am not going to ask you any kind of derivations in your exam paper. So instead what I do is I will show you the exam paper standard which I am asking. So hope you can see the exam paper. You see, every time once I ask the bosonic equation or something like that, what I give is I give all the formula. Don't worry. This time also I will give you all the formula. You know, no need to worry or remember all these derivational steps and the formula. You don't need to remind all those things, remember all those things, and then write all those equations by your own in the exam paper, right? All these equations will be there in the exam paper. What you have to do is you will have to calculate each and everything using this formula. You have to use the correct formula and plug the correct values given in the question and then answer correctly. That is what expected from you, right? So all the equations, right? This is also a bosonic formula we will be discussing soon. So bosonic theory. So this is for circular loaded, right? We will be discussing soon. So all the what I want to highlight is all the formula will be there in your exam paper. Don't worry, right? So it is not much challenging then, right? So what I want to stress is I am not expecting you to remind or remember all those formula. What I am expected from you is you need to know what sigma z is, what q is, what r, what is z, how to apply this formula, That is what expected from you, right? So I am focusing on delta sigma z only. I am not focusing on delta sigma x or delta sigma y. This is just for your information and knowledge only. Okay, right. So, so this is the formula we have discussed short while ago, right? So this formula is rewritten as follows, right? So the same formula I have um, rearranged and rewritten as below. What I have done is Q and Z square I have taken now. So that the balance part will be like this. I am not going to explain why. Now here if I take Q, here it will be 3. And then if I take Z square, 2, 5 will be remaining. So each and every term will be divided by Z square because I have taken out the Z square. So now if Z cube is there, the Z square is already taken out, so that here this part we have to take as Z, right? And then R square, RO Z is there, and then Z square is already taken. Actually here it should be Z, but because 5 divided by 2 is there, Z will be cancelling off. You may check it out if required. And then what I have done is Q divided by Z square is there. This whole part, if you check this one, there is no material property in it, like, gamma value or void ratio, porosity. Likewise, there are no material properties in this formula, this part. So this part, we say this is independent from all material properties. So we say this one as a shape function. So that's why we mention this as IB. So this IB value, we can get it as this part. The same part I have mentioned as IB. So that this equation is very simple now. Okay. So this is for point load. So I have a problem here. A kind of very practicing problem, very easy problem, and the equation also given here. What you have to do is a concentrated load of 1000 kilonewton is applied at the ground surface. You have to calculate the vertical stress at a depth of 4 meters below the load at a distance of 3 meters of the same depth. So here in the first question, now here directly under the point load, the depth is 4 meters. The other thing is same depth means 4 meter down and 3 meter away. So with that understanding, try to evaluate the stress with these values. So I will give you around 10 minutes. First you take 10 minutes break, and after the break you work on it, right? I will give you another 5 minutes and share your answers through chat box so that we can discuss together. Okay. First take 10 minutes break and have a cup of tea, and then come back, work on it, share me your answers. Okay. Thank you. Hello. Did you start working on it? Anybody? Ranmini, Sandamali, Asha, first room. If somebody started working, please let me know. Hello. No answers. Ranmini, you are there, right? Asha, Asha, you are working, no? Very simple. What you have to do is now the question is there. Certain values are also there. The equation is there. So you will have to plug the correct values in the equation and get the final answer. Okay. I will give you another 5 minutes. Please try to work on it and give me the answers. Yes, I received the answers from Ranvin. Thank you so much. How about the others? Okay. Now this one, uh, Q is 1000, right? Very clear. And then divided by Z square. Here 4 meters below the load. So the Z is 4 square into, we have our equation 3 divided by 5, right? 1 divided by 1, open bracket, 1 plus, here R is from here to here the distance. Now our point of interest is here. So that first question, the R value will be 0. So if R value 0, ROZ is also 0. So this part will be 0. So 1 plus 0 into the power 5 divided by 2, that is 2.5. So you get the answer. So very simple. 1 divided by 1, 2.5 the power. So as you all know, any power of 1 will be 1. So 1 divided by 1 then, right? So 1 divided by 1, the answer will be 1. So here we have 1000 into 3 divided by 4 square into 2, 5. So the answer 1000 4 square means 16 into 2 into 3.142. So the answer will be, Ranmini, you check your answer. It seems it is not correct, right? Here, as I said, R value becomes 0. So if it is 0, 1 plus 1 into the power 2.5 will be there, right? So here we have 1000 into 3. Here we have 4 square, that is 16 into 2 into 3, 3.142. Here this part will be 1. So the answer will be 29.83 kilonewtons per square meter. So you please check. Anyway, I really appreciate your effort, Ranmini. So the other question, the answer will be, right, 1000, same, point load is similar, 1000 divided by Z square, same depth, no? R square, open bracket, we have 3 divided by 25, right, into 1 divided by 1 plus, right? Here we have R. R is distance is 3 meter. 3 divided by 4. Here we have square, and then close the bracket. This is the open bracket, and then here we have 5 divided by 2, that is 2.5, right? So this is the answer. You just put this formula in your scientific calculator. So 1000 divided by 4 square into 3 divided by 2, 5. 1 divided by 1 plus 4, 3 divided by 4 to the power 2. Close the bracket. The entire power 5 divided by 2. Close the bracket. So that would be the answer for question number 2. So I didn't check the answer. So please check the answer and compare your answers with you all, so that you'll be getting the correct value, right? Okay. So this is the question number 1. So now with that, I hope you get a certain understanding how to apply this formula and calculate the stress distribution due to the point load, right? So with that, we will move on to the line load. Now, when we check the current situation of civil engineering, the point load nature, the nature of point loads is actually very rare, right? So compared to that one, normally we are getting line loads, and then sometimes mostly we are getting area loads. So the point load, the usage of point load and its associated formula is not much used in civil engineering. So that's why the line load has been incorporated in Bosonics equation, And Bosonic equation has been further developed to check the vertical stress increment due to the line load, right? So the line load, as you know, may be retaining wall, maybe a brick wall, maybe a tie beam. Likewise, there can be certain line loads applied. So these line loads will carry a certain kind of load per meter, load per unit length, right? So that as a result of this line load, now we are going to check what is the stress induced at point A. So when we check this line load, we have defined our 3D coordinate system at this line load. You see, now the x-axis has been defined perpendicular to this line load. Along this line load, we have y-axis, and then under the gravity, along the vertical axis, we will be having z-axis. So the three axes are there. So when we check about the soil element will be at x distance away along the x-axis and z distance below. I repeat, the soil element A will be placed x distance along the x-axis, means perpendicular to the load, and z distance vertically down, so that you will be finding your soil point. So if we have a soil point like this and the line load is acting like this, and from the line load the perpendicular distance to the soil is x and vertical distance is z, in such situation the vertical stress distribution at this soil point A due to this line load will be delta sigma z. So that will be um, sigma z is equal Q divided by Z into IL, right? So Q will be the unit load per unit length. Sorry, load per unit length. This load per unit length will be the simple Q. Okay. Then we have this IL, that is the shape function or influence factor. So that factor will be given by this formula. You can see, no? 2, 5, open brackets, 1 divided by 1 plus x divided by z to the power of 2, and close bracket to the entire power 2, right? So this is how this vertical stress inducement delta sigma z due to the line load q q per unit length, the line load in unit length. As a result of that line load, what is the stress inducement at point A? So the horizontal distance x, vertical distance is z. So there you will be having your point, soil point. So as a result of this unit load or line load, what would be the vertical stress induced, right? So that is what this formula results. So we have another practical problems. So this practicing problem is for, there is a certain point load here and also two line loads are there. So what you have to decide is, due to these two line loads and this point load, what would be the vertical stress inducement at this point A? In this figure shows two line loads and a point load acting at the ground surface. Determine the increase in vertical stress at point A, which is located at a depth of 1.5 meter. Now you know how to calculate for point load. Similarly, I have discussed short while ago regarding this line load as well. So with the line loads, with the point load, this is a kind of combination of loads. As a result of these combined load, what you have to calculate is the delta sigma z at point A, right? So as a combination of these load system, you cannot evaluate the stress at one glance. What you have to do is, first you have to evaluate the vertical stress increment at this point load. Because of this point load, what is the vertical stress increment at point A? Then you have to calculate, because of this line load 10 kilonewtons per meter, what is the vertical stress inducement at point A? Then you have to calculate, due to this line load 15 kilonewtons per meter, what is the vertical stress inducement at this point A? And then if you know the vertical stress increment due to this point load and line load 1, line load 2, you will have to add every stresses to check the overall impact at this point due to this loading system, right? That is how you have to calculate. You will have to individually calculate the vertical stress increment and then add together each of these stress values to have the combined effect. Okay. So now there are two equations. What you have to do is you will have to, excuse me. Give me 1 second. Okay. Sorry. Now you have two equations, right? So this is the questions we were discussing. So point load, two line loads are there. So there is a equation for point load. There's a equation for line loads, right? So if you have this equation and if you apply the correct values over there, you will be getting the vertical stress inducement at this point A due to this 30 kilonewton. And if you apply this formula and calculate what is the vertical stress inducement at point A, using this formula and applying the correct values related to this loading, right? And then if you apply this formula for this equation, this line load, you will have to apply the correct value and then correct depth so that you will be able to calculate the delta sigma z value for Q1 load as well. So you will add everything. Finally, you get the overall vertical stress increment at point A due to this loading system. Okay. Now let me check, let me calculate the point load with you, right? So the point load, this formula is there. So Q is the 30 kilonewton, 30, right? And then we have Z square. Z square is, now this is the point load. So what is the depth we are considering? 1.5 meter. So that is the depth we are considering. So 1.5 square, right? Into, we have a lengthy formula now. 3 divided by 2.5, right? Into 1 divided by 1 plus R. R is what? R is the distance from here to here, the diagonal distance. So from here to here it is 3 meter. From here to here it is 4 meter. So if so, what is the diagonal distance? Very clear. It is 5 meter using Pythagoras theorem. So now here we have 4 meter. We have 3 meter the horizontal distance. So if so, the diagonal distance is 5 meter. So R value is 5 meter. 5 divided by 1.5. 1.5. So there we will have to put a square. And then close bracket 5 divided by 2. Close bracket. So that's how you will have to calculate the vertical stress inducement at point A due to this loading. So you calculate this one and give me the answer. Thirty divided by if somebody get the answer, please share through chat box. No matter it is wrong, no matter it is right. What you have to do is please share the message. Check whether you received the point load, and as a result of this point load, the vertical stress inducement, the answer shall be 0.0125. 125 kilonewton per square meter. Kilonewton per square meter. Check whether you receive this answer, right? So that is clear now. So hope you understood, right? Now we are going to check uh, this point, this line load. So our equation is this one, right? So now here Q is 15, that kilonewton per unit length, no? So 15 is there. 15 divided by Z, 1.5. Okay. And then open brackets. We have 2 divided by 5. 5. And then into 1 divided by 1 plus x. What is this x? So here you see, this is the coordinate system. The horizontal distance to the point, that would be x, right? So that here, this is the point load. What is the horizontal distance? 2 meter, right? So here we have 2 divided by z is 1.5 depth, and to the power 2. Then we have another bracket here, to the power 2, right? And then close the bracket. So compared to the previous batch, I feel like the answers or responsiveness from this batch is little less. So please improve that one. Whenever I ask something, please give me answers. So if you have any clarification, please let me know. Previous batch was little bit better than this batch because they were more responsive. There were several students, they gave answers, they calculate by themselves. Actually, they perform really well in the exam. Most of them got A plus and A's, right? So really better to work with the lecturer. So I request you to work with me and give me the answers, right? So then only you will understand how to apply. What is X? What is Z? What is Q? Likewise, then only you can understand what's the principle or what's the application of this formula, right? Okay, please calculate and give me the answer. So, anybody got the answer? So, I received, I don't know whether it is correct, 0.825. You check with your answers. Sometimes there can be some calculation errors from my side as well. So you better check with your answer and compare the answers for the correctiveness, right? Okay. So that is for the line load number 1. So similarly, you can calculate the line load number 2 is there. So similar principle. Here instead of Q2, you will have to apply 10. Depth unchanged, no changes are there. And the R value for this one, R value will be 4 because from here to here the horizontal distance is 2 plus 2. So that will be 4. 4 divided by 1.5. That would be the change. So with that, please get the answer. So I received the answer 0.0645. Let's say 4 kilonewton per meter square. So these are the answers. Finally, the total value will be the addition of these three. Total will be the addition of these three. 0.0125, 0.825, 0.064. So all together you add and get the final value, right? So that would be the vertical stress increment delta sigma Z due to this point load and this line load and this line load. Okay. So is it clear? I hope that is clear to you. If you have any doubt, please let me know. Any doubts? Is it all clear? Nobody is answering. Hello. Is that clear to you all? I prefer if you talk to me. Asha, Ranmini, Sandamali, is that clear? Okay. Right. Anyway, I'll be giving you some kind of same similar questions in your exam paper. So if you don't understood it well in the class, it will be difficult for you, right? So anyway, I'll be strict in the marking, so I cannot give you free marks. So that's why I time to time ask you, if you don't get this one, if you have any clarifications, please let me know, something like that. So, but anybody, if you have any problem, please let me know. Okay. So everybody is happy. Then we will move on to the next slide. So next slide also the similar thing. As you can see, there's a point load and two line loads and same distances. What I have asked you to calculate the vertical stress increment delta sigma Z due to this loading system, right? Point load, you will have to use this formula. Two line loads, you will have to use this formula, so that get the individual impact at point A and then get the combination by adding each and every stress values. So that finally you will get the combined vertical stress increment due to this loading system at this point A. Okay. I'm not going to discuss this question because it is very similar to the previous example, right? So what we have discussed was, now we have discussed um, the vertical stress increment for a given load uh, using the Bosonics equation. There we discuss about the point load and the line load, right? The point load we discuss about a formula and its applications. So I am at office for election. Ah, really? Sorry. Sorry for the uh, right, right. Asha, you are there in the election duty, no? Right. It's fine. It's fine. So anyway, if you have any question, or if you need any clarification, please send me a message through chat box, so that I can get updated with your understanding, right? Okay. So Bosonic equation we have been discussing, right? So now the point load is there. So as a result of point load, the vertical stress increment we already discussed, and this is the formula we were discussing. So IB, there's a separate function for Bosonic equation. So we will have to refer to that for this IB, the shape function. And the line load also, there is another formula. So we have already discussed about these two. But the sad story is as civil engineers, we are rarely having this situation for point loads and line loads. Most of the structures we are constructing, they exert area loads only, right? So there we have to discuss about the area loads now. So point loads are there, line loads are there, but practically we are not frequently seeing these kind of loads like point loads and line loads. Instead, we have area loads in most cases. So that's why we are now going to discuss about uniformly loaded circular area, uniformly loaded rectangular area, trapezoidal and triangular load, right? So we will be discussing about the uniformly loaded circular area today. So if we have time, we will be discussing about uniformly loaded rectangular area, and then we will be discussing about trapezoidal and triangular load area tomorrow, right? So today we are going to discuss about uniformly loaded circular area. So if the time permits, I will try to complete this area within today, right? Okay. Now, stress under uniformly loaded circular area. We are going to discuss about this part. As you see, some of the structures that we are creating or we are building or constructing are of the circular area nature. For example, a circular type water tank. Overhead water tanks are there, no? So if you are working with water supply and drainage board, or if you are living in a area where the water supply and drainage board projects are there, so there you see some types of water tanks, no? Hugely constructed elevated water tanks, all are in round shapes. So what happen is, as a result of these structures, the load will be exerted on the ground with a circular footing or circular foundation. So in such situations, what we have to do, what we have to use is this formula, right? This is also a extension of Bosanik's is equation, right? So Bosanik has developed his equation for point loads, but it has been further developed for line loads and this circular loaded area as well, right? So in case we have a circular foundation, we will have to use this formula. So we have two cases. In case of a vertical stress under the center of circular footing. Now let's say this is the circular loaded area. This is at the center. This is the center. So the circular area, the radius is capital R naught. So if you consider any point down the center of circular footing and evaluate the vertical stress increment due to this foundation load. So in such situation, you will have to use this equation. I repeat. So let's say you are having a circular foundation. There the radius is R naught, right? So now you will have to evaluate the vertical stress increment due to this loading system directly under the center of this foundation. කේන්ද්‍රය යටම තියෙන පොයින්ට් එකක vertical stress එක හොයන්න තමයි ඔයාට කියන්නේ. So in such situation, what you will have to do is you will have to use this equation and calculate the vertical stress. So this is more or less similar to our previous equations for point loads and line loads, but there's a this small difference there. We will be checking now. So now here delta sigma z is equal to Q. Q is the applied vertical stress in this foundation, right? The UDL or load per unit area, that load. And then 1 minus 1 divided by 1 plus R naught, capital R naught. R naught is the radius of this loaded area, divided by this Z. Z is the vertical distance or depth into square or close bracket to the power of 3 divided by 2. Right? So that is how we are going to calculate the vertical stress due to this circular loaded area. Okay. So case B. So in case of directly under the circular footing, we have to use this formula. But what happens if you are interested another point in the soil? Means the point is not under the center. It is away from the center. So in such situation, due to this loading, what would be the stress induced at this point? So that can be derived using this formula. So delta sigma Z is equal to Q into IZ M comma N. You may wonder why this is. What is this? So this is a kind of shape function, Lamai. So what you have to do is, you will have to get this value using a graph. I will show you the graph. Before that, you will have to understand what this M and N. So M stands for Z divided by R naught. Simple N stands for R divided by R naught. Z is depth, R naught is the radius of the loaded area. And then simple R is for the distance from the considered point to the center line. Now this is the center line, right? From here, what is the horizontal distance to the considered soil point? That would be simple R. R divided by R naught. Capital R naught is again, it is the radius of the circular loaded area, right? So if you know M, if you know N, then you will have to refer to IZ, that is for shape function and influence factor. So that will be given by this graph. Okay. So now I am going to discuss with you regarding this graph. So it is very easy. Now you see, so this is the circular loaded area. Every notation is there. Don't worry. So B is from here to here, that is the diameter. Diameter is equal to 2 times R naught. What is that? R naught is the radius of the loaded area. That is very clear, no? R naught is the radius of the loaded area. And simple Q is the contact pressure. So from here to here, the depth is Z. From here to here, the horizontal distance is R. So this is the point you desire. So you are going to evaluate the vertical stress increment at this point due to this Q area load. So that vertical stress is IZQ. Q is the applied pressure, IZ is the shape function. Now I am going to teach you how to evaluate this IZ using this graph. It is really easy. Okay. Now you see several graphs over there. Okay. Now this is a kind of graph paper. Here you will have y-axis. So the y-axis is reference for depth Z divided by R naught. Z divided by R naught. And also there you will be having some inclined graph. So inclined lines are for, here you have R divided by R naught. Numbers on curves indicate values of R divided by R naught. What is R? R again I say the horizontal distance to the desired point. R naught is the radius of the loaded area. Okay. So R divided by R naught is there, so that, so these inclined lines you know how to find. And then if you know the Z divided by R naught, you can calculate, no? Right? If any question is given to you, you will be given with the Z depth. Also, you will be given with the R naught, the radius of the loaded area. So that you can calculate the Z divided by R naught. If you know the Z divided by R naught, let's say it is 3.5. Okay. So if it is 3.5, the value will be somewhere here. 3.5. Okay. This is 3, this is 4, 3.5 is somewhere here. And let's say your R divided by R naught. R is here, this one, the horizontal distance, it is given in the question. And R naught also given in the question. So in that situation, you can calculate the R divided by R naught. Let's say it is also 3.5. So what you have to do is, now this is 3 and this is 4. 3.5 is somewhere mid of this. Okay. So you interpolate that one and draw this line until it intersect the correct R divided by R naught, this inclined curves. So you go up until you find the corresponding I value. So this is the IZ value, influence value, right? This is the influence value. So here it is 1, here it is 2, this one 2 point, let's say 3, 2.3. So the value will be there, sigma Z is equal to 2.3 times Q. But remember, this is stress in percent. It is in percentage. So 2.3% of Q means the value will be 2.3% of Q. You understand how to do that, right? 2.3% means 2.3 divided by 100 into Q. Got it? So that's how we evaluate a given stress using this graph. Is that clear? Anybody who can talk, please let me know. Anybody who can send me message, please let me know whether it is okay. Actually, today attendance is very less. I don't know why it is so. Is that clear? Can you send me some messages or raise your voices? Sandamali? Okay, Asha. Very good. Okay, now it is like this, Asha. Right? Now I mentioned the vertical stress under the center of circular footing. You can directly use this formula. No issues. So that is clear. And vertical stress at any point in soil. That means now this is the, let's say this is the base of circular water tank, right? So as a result of this circular water tank, you want to know the vertical stress at this point. So this is not under the center. This is not under the center, right? So this is not under the center means this is somewhere else, right? So that's what we are using this graph. So how to evaluate this graph? You have to use Q into IZMN. So Q is the applied pressure, that is fine. This IZMN will be uh, obtained by a graph. So this is that graph. Okay. So now how to evaluate the IZ value? If you know the IZ value, you can know the sigma Z value as well, right? That is the vertical stress due to this circular loaded area. this vertical stress, in order to evaluate the vertical stress at the given point, what you have to do is you will have to evaluate this IZ value using this graph. Okay, so let me clear this area first. Right? Okay. Now remember, this is the circular loaded area. The radius of the circular loaded area is capital R naught. And this is the point you are considering, you are interested. So what you are going to do now, because of this Q area load, what is the vertical stress increment at this point? That's what you are going to calculate. So this Q, you know, this Q, you know. Now what you have to do is, you will have to evaluate IZ. Then only you can calculate the sigma Z value. Now how to evaluate IZ? That's what I am going to tell you now. First, in this graph, in this vertical axis, you will have Z divided by R naught. So what is Z? Z is the depth. R naught is the radius. Okay. Let's say in a given question, Z has been given as 5 meter. R naught, the radius of the loaded area, has been given as 2.5. So what is the Z divided by R naught value? Z, the depth is 5 meter. R naught is 2.5 meter. If so, Z divided by R naught is 2. Okay, that is an example. So let's say the value is 2. This one. So what you have to do is, now you calculate the Z divided by R naught value. Then if you see, there are certain curve line. So these curve line are for R divided by capital R naught. Simple R divided by capital R naught. Simple R is this one. Now this is the center. From this center of the loaded area, what is the horizontal distance to the considered soil point? That is simple R. And R naught is the loaded area radius. We are considering now circular loaded area, no? So that's why we are considering the radius. Now, let's say simple R is 5 meter. R naught, let's say 2.5 meter. So in that situation, simple R divided by R naught is 2. Now you have 0, 0, 2.5, 0.25, then we have 0.5 line, 0.75, then we have 1, 1.25, 1.5, 2, 2.5, like that. There are several graphs. Okay. So now in this question, in my example, I said simple R is 5, capital R is 2.5. Let's say like that. So in that situation, R divided by R naught is 2. Means this is the graph that is referring to us. Okay. So in that situation, this curve line referring to our example is this one. So now what you have to do is, now your Z divided by R naught. This value, for my example, it is 2. So you will have to have a horizontal line like this until you find the corresponding curve line here. So this is the point of intersection. At the point of intersection, you go up until you find corresponding IZ value. Now, what is this IZ value? As per this example, 1, 2, 3, 4, 5, 6, 7. Here it is 7. Okay. So, this is what? This is the IZ value, but it is mentioned like this: is stress in percent of surface contact pressure. This is a percentage value, means this value is 7%. Okay, so now you apply 7% here. 7% into Q value. Q will be given in the question, right? 7% means 7 divided by 100 into Q. So final value is this one. This is the sigma Z value. Clear now? Is it okay? Asha? Now okay, no? Right. Okay, good. Right. So now you know how to evaluate the loading for uniformly loaded area, circular area, so that if the point of interest is directly under the center of 14, if it is directly under the center of this circular 14, it is really easy. You can use this equation. In case it is not directly under the point of center and it is somewhere else, in that situation you have to use this graph, which is also very simple, right? You will have to evaluate Z divided by R naught, and then you will have to evaluate R divided by R naught. So with that, you will have the point of intersection, and you go up, take the corresponding IZ value, so make it in a percentage and evaluate the final stress value. Very easy. So this is a question for you, right? So kindly get a screenshot of this slide and then try to work it on at office or in your as a homework. So tomorrow when we are meeting, we will be discussing about this theory once again, and we will be discussing this question. Okay, so ask your friends to join tomorrow, right? So because this is a very interesting topic, so that tomorrow we will be discussing about circular loaded area once again, and we will be discussing about this question once again, and then rectangular loaded area again, right? So the new topic tomorrow will be rectangular loaded area. So I am expecting to cover this rectangular loaded area, this slideshow, and uh, hope you will be understanding these principles as well. Okay. So now what we discussed today was we discussed about the stresses. There we discuss about certain stresses are generating due to sulfate of soil material, and also due to several structures we make. So first we discuss about the sulfate, how to evaluate the stress due to the sulfate of soil material. And then we discuss about the approximate method for external loads. So various loading we are creating on the ground as a result of this various loading due to the rectangle loading. What would be the vertical stress increment? We calculated using the approximate method, 2 to 1 method, right? Then we discuss about the Bosonics theory for point loads, line loads, and then finally the circular load. So hope you get a certain understanding. So today I am not happy about the class. I should say that to you because many of you are absent. I really appreciate those who uh, had the participation today throughout the lecture. So hope you get a certain understanding. Tomorrow we are going to discuss a kind of very important topic that would be a circular loaded area and rectangular loaded area. If we have time, we will be discussing about triangular loading area and trapezoidal loaded area. All those things are very interesting topics. So I hope tomorrow morning you will be joining with me. So please join and get certain understanding on these principles, because in your exam paper there will be one or two questions from this area, right? So it is very important. So hope you attend, because finally don't call me and ask, please sir, give us additional lecture and clarify these questions or these lecture content. Like that, I received several calls in previous batch, but I couldn't do with my time schedules, right? So I hope you attend on the classes and have a kind of good knowledge with these principles and theories. Okay. So I hope you will all participate tomorrow lecture. Please share the message to your colleagues that to attend tomorrow lecture. So I will conclude from this slide. So we will be meeting tomorrow morning. So thank you for joining everybody. I will wind up the session.